In this class, I am going to discuss about few notations which are used widely in physics. First, the notation of Resnick and Haliday. This is an encircled dot. A dot is sitting within a circle. Now this means upward direction. Direction towards reader, which means it is a direction away from paper. In short, we can say that it is upward direction, up. Another notation of Resnick Haliday is an encircled cross. So a cross sitting within a circle. This means a direction into the paper. In other words, it's a direction away from the reader. So it is a downward direction. So encircled dot is upward direction towards the reader, away from the paper, and encircled cross is a downward direction into the paper, away from the reader. These notations are frequently used to specify direction of a vector. Now I will discuss an extremely useful symbol which is called Kronecker delta symbol. The first point is Kronecker delta symbol is used for discrete or discontinuous variable. For instance, let us consider a variable a, and suppose it takes or assumes values -1, 0, 1 and so on so forth. Or another variable b which also assumes the same values -1, 0, 1 and so on so forth. Now if this is so, then we can define Kronecker delta symbol as delta AB. So this is the symbol of Kronecker delta. Now it will be 0 if A and B are not equal, and it will be equal to 1 if A and B are equal. So this is the definition of Kronecker delta symbol. Let us give example. Kronecker delta of A3. What will be its value? Now Kronecker delta A3 obviously, as per this definition, will be 0 if A is not equal to 3. But if A happens to be equal to 3, then its value is 1. Let us cite another example. Delta B minus 2. So here 2, this is equal to 0 if B is not equal to minus 2. But if B equal to minus 2, then the value of this Kronecker delta is 1. What is the value of the Kronecker delta symbol? Delta 1 1. Now here we see that 1 and 1, they are identical integers, so this is equal to 1. What will be the value of delta 1 0? Since 1 and 0 are two different integers, they are unequal, so delta 1 0 is 0. Kronecker delta symbol is an extremely useful concept having numerous applications in physics, and we'll come across them. Before going into problems, let me reiterate that Kronecker delta symbol holds for discrete or discontinuous variables. Here minus 1 and 0, between these two integers there is a huge jump. They are separated, they are not continuously varying. A is not continuously varying, so for this situation Kronecker delta symbol holds. But if A assumes continuous values, then we cannot use Kronecker delta symbol, and instead of Kronecker delta symbol we will be using Dirac delta function. Dirac delta function is used for continuous variables, say x. Suppose it varies from minus infinity to plus infinity. So under this situation we cannot use Kronecker delta symbol or function, but we have to use Dirac delta function. Now what is Dirac delta function? We will discuss in a separate video in details. Now let me come to solving some problems involving Kronecker delta symbol or Kronecker delta function. Evaluate summation over I Kronecker delta I to AI. We note that summation is over the dummy index. Summation is over the dummy index or run index I, and I assumes values minus infinity to plus infinity. It assumes various integral values. And therefore we can split this sum into two parts. The first part is when we sum over infinite number of integers except I equal to 2, and since we cannot leave I equal to 2 out, let us write it separately. Now Kronecker delta I2 for I not equal to 2 is 0. So this is 0, which means the first term is not there. Now here again the property of Kronecker delta is that Kronecker delta I2 is 1 if I equal to 2. So this is equal to 1. So the answer will be A I for I equal to 2. So the answer will be A 2. So this is the answer. Now here we find that on the left hand side there was a summation, but presence of Kronecker delta has removed the summation. So the formula is 1 Kronecker delta, or property is 1 Kronecker delta knocks out or removes one summation. Let us do another problem. Evaluate summation over I, summation over j, Kronecker delta ij, a I j. Now here there are two summations. So let us first perform summation over j, and after having performed summation over j, we will focus our attention to performing summation over I. Now when we perform summation over j, we come across two parts. One is summation over j not equal to I, and we'll have one term which is Kronecker delta ij, a ij, but this corresponds to j equal to I. This term was left out when we considered this sum. Now this Kronecker delta ij is obviously 0 for I not equal to j, so we do not have this term to survive, and here Kronecker delta ij for j equal to I or I equal to j is 1. So we can write summation over I, a I, because here j equal to I. So this is the answer. We note that on the left hand side we had two summations, but on the right hand side there is one summation. Where did one summation go? One summation, which is not present here, has been knocked out by the Kronecker delta. So one Kronecker delta will knock out one summation, and this is very evident from this problem. Let us consider a note. As mentioned, Kronecker delta 1 1 is 1. Kronecker delta 1 2 will be 0 because 1 and 2 are different. Kronecker delta 2 1, again 2 1 is different and therefore it is 0, and Kronecker delta 2 2 is 1. Now these results can be combined and written as we combine this and write it in a matrix form. So delta equal to Kronecker delta 1 1, Kronecker delta 1 2, this is 2 1, this is 2 2, and delta 1 1 is 1, 1 2 is 0, 2 1 is 0, 2 2 is 1. So what we get is a unit matrix. And since a matrix is an operator, we can put a operator sign here also. Now this holds for two indices. So this note holds for two indices. And what are the indices? The indices are I and j. And I represents 1, 2, and j also assumes values 1 and 2. So for two indices, this is the shape of Kronecker delta symbol or function. Let us extend this idea. So for three indices, I, j and k, running over 1, 2 and 3, let us construct the matrix. So the first row, first column is 1 1, first row, second column, Kronecker delta 1 2, first row, third column is Kronecker delta 1 3. And similarly we have second row, first column, second row, second column, second row, third column, and finally third row but first column, third row, second column, third row, third column. And the values are very easy to find. 1 1 is 1, then 1 2 is 0, 1 3 is 0, 2 1 is 0, but here we have repeated indices, so this is 1, then we have 0, 3 and 1 are unequal, 3 and 2 are unequal, but 3 and 3 are equal, so here we have 1. So again we arrive at unit matrix. Also note that there are, for two indices, 2 square is 4 components, and they are 1 2 3 4 components, but here we have 3 square equal to 9 components. And the components are Kronecker delta 1 1, Kronecker delta 1 2, Kronecker delta 1 3, then we have 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. So there are altogether 9 components, which are all Kronecker delta symbol, and their values have been extracted here, written here. A word about use of Kronecker delta symbol. So Kronecker delta symbol is used to express laws in a compact form. I'll just mention one example. Orthonormality relation, which we will discuss in a later video. There is a very important relation involving the unit vectors, say E1 cap, E2 cap, E3 cap, and they might be I cap, J cap, K cap, or you can write in terms of x, y, z, x hat, y hat, z hat. The orthonormality relation is given by EI cap dot EJ cap is equal to Kronecker delta. We'll discuss this in a later video. Having defined Kronecker delta symbol, let me define another symbol which is also used, and that is called Levi Civita symbol. Levi Civita symbol is denoted by epsilon ijk. So, unlike Kronecker delta, which involve two subscripts, Levi Civita symbol involves three subscripts, say I, J, K. Now, if two indices are equal, say epsilon 1 to 2, say here also 2 are equal, in fact all 3 are equal, then the value is 0. So this is one possibility. Another possibility is if I, J and K are cyclic, say epsilon 1, 2, 3. So after 1 comes 2, then comes 3, and after 3 comes 1, so it's cyclic. Then the value of Levi Civita symbol is 1. Let us consider 3. After 3 comes 1, and after 1 comes 2. So this is also equal to 1. Epsilon 2, then comes 3, which is followed by 1. So this is also 1. If the other possibility is if I, J, K are anticyclic, for instance epsilon 1, 3, 2. So after 1, 2 should have come, but we have 3. So the cycle is broken. The cycle is 1, 2, 3, 1. So here after 1 comes 2 should come, but here 3 is there. So the cycle is broken. So in such situation the value of it will be minus 1. Similarly epsilon say 3, 2, 1. So we see that after 3 1 should come, but here we find 2. So it is anticyclic. The rule, the chain is broken. So the value of it is minus 1. Now the role of epsilon ijk is that it expresses laws in compact form. So epsilon ijk expresses laws in compact form. We'll mention one example for unit vectors. Where I, J runs over 1, 2 and 3. So the cross product of unit vectors ei cap and ej cap can be written as epsilon I, J, K into ek hat. So instead of writing so many relations, we can write a single relation using Levi Civita symbol. Now we'll discuss these relations, we'll prove these relations in later videos. It can be shown that Levi Civita symbol epsilon I, J, K has 27 components. Let us write down the 27 components. So there will be three components which involve cyclic occurrence of the numerics 1, 2 and 3. 1, 2, 3, 2, 3, 1 and 3, 1, 2, and Levi Civita symbol has value 1 for them. There will be three components which involve anticyclic occurrence of these three numerics 1, 2, 3. For instance, 1, 3, 2, the cycle is broken here. After 1, 2 should have come, but we have put 3 here, and its value is -1. Similarly, epsilon 3, 2, 1 and epsilon 2, 1, 3. And the remaining components, there will be 21 in number, will have repeated occurrence of the numerics 1, 2, 3, and then the value is 0. Let us mention them. Say all are same. So this is one possibility, and then we can think of the other possibilities. Say 1, 1, 2, 2, 1, 1, 1, 2, 1. The pattern is we have written down the numeric 1 twice, and there are also other options 1, 1, 3, 3, 1, 1, 1, 3, 1. Now we will write down, instead of 1, 2. So we have 2, 2, 1, 2, 1, 2. The remaining terms will involve repetitions of 3. So we'll have epsilon 3, 3, 1, and then 1, so 2 will be there. So we can count them. One, 2, 3, 4, 5, 6, 7. 7 3s are 21. So altogether there are 27 components. Of Levi Civita symbol epsilon ij